And so our last talk of this session is Hyunbae Park, crucial factors of Lyman alpha transmission in the reionizing intergalactic medium.
Hi, you hear my voice and see my screen?
Yes, we do. Thank you.
Okay, thank you. I'm Hyunbae Park from Kavli IPMU. First of all, I'd like to really thank the organizers for this great conference and the opportunity to present. So this talk is about HII-region transmissivity of Lyman alpha photons during reionization based on the CODA2 simulation data. So just for a brief introduction, Lyman alpha emission from high redshift galaxies is considered as a promising probable reionization history because Lyman alpha photons are easily scattered off the line of sight by neutral hydrogen gas in the intergalactic medium. So recent observations do find that the chance of finding LAEs decrease steeply above redshift 6, especially for relative faint galaxies. There are some preliminary constraints on the HII neutral fraction based on these observations, although they have not converged yet. So when future experiments like JWST launches, we expect to have a huge development on these subjects. So the motivation of this work is to try calculating the Lyman alpha transmissivity in a simulated IGM to quantitatively understand how the IGM during reionization affects the observability of LAEs. In this regard, the CODA2 simulation provides high-resolution data of IGM during reionization in a fairly large volume. In the simulation, the cold dense gas is converted into stars with some prescriptions, and the ionization by these stars is computed simultaneously with its feedback on the IGM to produce density, velocity, and temperature field that we need for calculating the Lyman alpha opacity. So you can find the details of these great simulations from the Osberg et al. 2020. So here are H1 density maps at different scales for a galaxy at redshift 7. Blue is neutral, red is ionized. So I assume the IGM around the galaxy is defined as the gas outside the video radius and calculate the optical depth by integrating the cross-section times H1 number density outward from there. So the Lyman alpha cross-section is largest at the line center, of course, and then it also has a damping tail extended outward. So every photon emitted on the blue side of the line center will be scattered eventually because they will redshift into the line center at some point where the cross-section is very large. But then also a fraction of photons emitted on the red side will be scattered too in the neutral IGM because of this damping wing opacity. And this damping wing opacity depends sensitively on the H2 region size because the more photon redshift away from the line center in the H2 region, the lower the damping wing cross-section is. So we look at the transmission curve for this particular line of sight, shown as the green arrow in the lower center panel. And the transmission curve has typically has a shape of a step function where the transmission is 0 below certain wavelengths and non-zero but below 1 above certain wavelengths due to the damping wing opacity. So interestingly, the line center absorption extends to the red side of the line center because the IGM around galaxy typically gravitationally infalls toward the center, blue shifting the photons in the rest frame of the IGM. So the location of this transmission cutoff indicates the maximum IGM infall velocity around the source galaxy. So in the lower right panel, I create a model double peak profile for the intrinsic emission coming from the galaxy and multiply that to the transmission to obtain the observed line profile shown as the solid line. Typically, the blue emission is completely suppressed, and some part of red peak is also truncated by this infalling IGM. So here, here are the transmission curves for different sightlines for 3 galaxies with different halo masses at redshift 7. If you focus on the location of the cutoff, you see that the offset between the cutoff and the line center are larger for more massive galaxies. So this is because more massive galaxies have stronger gravity, leading to stronger infall motion. In the lower left is the probability density distribution of this infall velocity, which shows basically the same trend. And the lower center plot shows the infall velocity as a function of halo mass. And here the error bars on each data point is 1 sigma range obtained from 2000 sightlines for each galaxy. So we find that basically this infall velocity is very similar to the circular velocity of the post dark matter halo with some scatter. And the UV magnitude also has a similar relation with the infall velocity because it correlates with halo mass. I move on to the damping opacity on the red side of the cutoff. The neutral density maps around the same galaxy redshift 6, 7, and 8 shows the increasing neutral fraction in the IGM toward high Z. So the transmission curves at the bottom show that the red side transmission decreases toward the high redshift. So the evolution in the transmission is obviously coming from the ionized regions becoming smaller toward higher redshift. The median distance from the galaxy to the bubble edge, the RB, is larger for galaxies at redshift 7 than that at redshift of 8. And the dotted curve here in the right panels are the corresponding transmission curves for those median H2 bubble sizes. And also we compare bright and faint galaxies to understand why LAEs are more difficult to find in faint galaxies at high redshift. So in the H2 density maps here on these two groups, the difference is not as clear as in the redshift dependence, but if you see carefully, faint galaxies are more likely to reside in small H2 regions than the brighter ones do, presumably because they emit less ionizing photons. So these maps tell us how complex and diverse the H2 region shape can be in reality. If you compare the median transmission curves in the right panel, see there are two differences. So first, the transmission cutoff appears at a shorter wavelength for fainter galaxies because they're less massive on average and the infall motion is weaker. And also the transmission on the red side of the cutoff is lower for the fainter galaxies because the H2 bubble sizes are smaller for them. So here we multiply the transmissivity to the model emission profiles. We give a broader line profile to brighter galaxies because they're expected to require a larger frequency offset for the photons to escape the galaxy. So these results have a number of interesting aspects. So first of all, some part of emission is still scattered by the infalling IGM, even at redshift 6, where the IGM is almost fully ionized. And then the transmission of the red side of the cutoff decreases toward high redshift. And you can see that brighter galaxies are relatively less suppressed than the fainter ones do, which is consistent with the observation. And there are two reasons for this. One is the difference in the bubble size. Brighter galaxies are in larger H2 bubbles on average. And the other is that the brighter galaxies transmit redder photons because of the stronger infall motion and larger offset in the intrinsic profile. So basically, the redder photons are subject to less opacity for given bubble size. And I find that these two factors are comparably important in the UV magnitude dependence. Now I would like to list some interesting cases I found in the analysis. So in this example, I'm showing two sightlines shown as dotted lines here that are only 3 degrees apart, but the transmission is almost 4 times lower for one of the sightline. And what's happening here is that one of the sightline goes right through a dense self-shielded neutral gas system inside the H2 region, shown as this blue region in the map, where the transmission is highly suppressed. And we expect to have a lot of such self-shielded systems during reionization. So this case demonstrates how Lyman emission can be suppressed even in highly ionized regions. This is another interesting case. So this sightline, this faint dotted line, goes right through an extremely low H1 density blob, shown as dark red in this map. This blob was created by supernova explosions in the neighboring galaxy, and H1 density here is so low that photons can be transmitted even when they're at the line center in the rest frame of the IGM. As a result, some photons leak through this window, creating a double peak like feature in the spectrum. But this is pseudo double peak because both peaks actually come from the same red peak in the intrinsic profile. So there are currently a few double peak LAEs observed around redshift 6, which call for explanation. I think this case makes an interesting potential scenario for them. So here are the full statistics of Lyman alpha transmission as a function of UV magnitude from CODA 2. And by taking the ratio of redshift 7 and 8 result, this black lines for the median, to the redshift 6 result, we obtain the relative suppression by the neutral IGM shown in this table. And you can basically see the redshift and UV magnitude dependencies, which I already discussed. And I'd like to lastly briefly talk about the variance in this relation shown as the gray shade. So the variation in the transmission comes from the complexity of H2 bubble shape, making it difficult to constrain the average transmission with a small number of observations. So if we take the ratio of the 1 sigma range to the median value, it is greater than 1 for most galaxies at redshift 7 and above, which means that we need more than 100 galaxies to suppress this variation to 10% level. And the current constraints are at above redshift 7 are based on less than 100 galaxies. So I think this may be why the constraints have not converged yet. But of course, future experiments like JWST and NGRST and Euclid will improve on this by enlarging the sample size. And according to our results, brighter galaxies have relatively smaller variation in the transmission. So in that sense, maybe NGRST and Euclid might be more efficient because they're more focused on brighter galaxies in the wider fields compared to JWST. Yeah, so I quickly listed my findings from the CODA2 simulation. I'll leave the summary slide on and take questions. Thanks for listening.
Thank you, Hyunbae. Very nice talk.
Yeah.
Hi, Hyunbae. Very nice talk. So I'll ask first question. What is the Lyman alpha escape fraction below the resolution of the simulation?
I don't think the simulation assumes any Lyman alpha escape. Actually, the simulation does not simulate Lyman alpha photons. It only simulates the ionizing photons, and there's an escape fraction for the ionizing photons. And I basically calculate the Lyman alpha transmission using the ionization field and density field produced by the simulation. Not sure I'm answering the question.
I guess a follow-up is: do you have any ISM or CGM absorption or attenuation on the Lyman alpha, or are you assuming all the Lyman alpha that's made in a galaxy gets out and is then susceptible to IGM absorption?
Oh yeah, so yeah, I'm basically assuming CGM and ISM as a black box because it's not well resolved by the simulation. So yeah, as I showed, I'm only assuming a simple double peak profile. Basically assuming that I don't know anything about what's happening in the CGM.
Okay, does your intrinsic Lyman alpha luminosity depend on the escape fraction of ionizing photons?
Could you repeat that? Actually.
Yeah, does your intrinsic Lyman alpha luminosity depend on the escape fraction of ionizing photons?
So Lyman alpha luminosity, we do not assume any Lyman alpha luminosity here. We only assume the shape and calculate the ratio between the shape without any normalization, and to get the fraction of Lyman alpha photons that escape. So yeah, we will get to that part in our next studies.
Okay, another question has to do with double peak sources, or really sources where you see blue emission. Can you quantify how common or rare those sources like COLA 1 should be?
Yeah, so I can talk about this pseudo double peak feature I found from the simulation, and I would say it's rare, and I kind of found this by eyes going through different transmission curves. But it's not impossibly rare. I find it maybe 1% of the time from different transmission curves, and I think this is another interesting thing to expand upon using the CODA2 simulation data. I'm going to explore that further.
Is the simulation targeted to produce high overdensities to compare to observations?
So CODA2 has fairly large volume of 64 megaparsec over H, and it definitely has overdense regions with large H2 bubble, and I know there are observations suggesting on overdensity of galaxies with presumably large H2 region, And I think that's another interesting topic to study with CODA too.
All right, I'll ask one more. Do you need to consider the metallicity of the gas at these high redshifts?
So I think in the IGM, we don't have to, right? So there may be some metals in CGM and ISM, but maybe we can almost assume in the IGM, there is no metal. And that's what I'm calculating here for now.
Okay, I'd like to thank the speakers again for giving some very interesting talks. This concludes session 2B, and we'll see you for session 3. Thank you very much, everybody.